The compartmentalization of NAD within the cell into nuclear, cytosolic, and mitochondrial pools is a fundamental yet often overlooked aspect of NAD biology. These compartments are not simply arbitrary physical spaces. They represent metabolically distinct zones with different NAD consumption rates, enzyme expression profiles, and functional implications. Nuclear NAD regulates DNA repair via PARPs and epigenetic modifications through sirtuins like SIRT1. Cytosolic NAD drives glycolysis and redox homeostasis, while mitochondrial NAD is essential for ADP production and cellular respiration. The question of whether different NAD precursors preferentially replenish one pool over another, particularly whether NR and NMN hold an advantage in mitochondrial compartments over niacin, is complex and more unsettled than often portrayed. All NAD precursors eventually aim to elevate intracellular NAD levels, but their entry points and conversion enzymes differ. Niacin, nicotinic acid, uses the Price handler pathway involving nicotinic acid phosphorybosal transferase, NAPRT, NMNAT, and NAD synthetase, largely active in liver, kidney, and immune tissues. NR and NMN use the salvage pathway, entering through NRK1/2 for NR, or presumed extracellular dephosphorylation followed by NEMPD for NMN, ultimately relying on NMNAT1/3. Importantly, NMNAT1 is nuclear, NMNAT2 is cytosolic and axonal, and NMNAT3 is thought to be mitochondrial or associated with mitochondrial membranes. This anatomical enzyme distribution suggests that the site of conversion, and hence the location where NAD levels rise first, depends on the precursor and the cell type. Animal and cell culture studies suggest that NR may preferentially boost cytosolic and nuclear NAD, especially in tissues with high NRK1 expression, such as liver and muscle. NMN's activity is less direct. It's rapidly dephosphorylated to NR in the gut and circulation, then reconverted intracellularly. This means that despite theoretical pathways showing NMN entering cells intact, in vivo much of its action is functionally similar to NR, a point sometimes downplayed in supplement marketing. In contrast, niacin increases NAD more broadly through its liver-centric Price handler pathway, resulting in systemic elevation of NAD and its precursors such as NEAD, which may redistribute among compartments based on downstream demand. As for mitochondrial NAD, the evidence is much more ambiguous. Mitochondria do not import NAD directly, and the presence of NMNAT3 in the mitochondrial matrix has been difficult to confirm in humans. In mouse models, NMN or NR supplementation modestly boosts mitochondrial NAD in muscle and liver, but the effects are inconsistent and highly tissue-dependent. Some studies show that NR fails to elevate mitochondrial NAD in aged tissues, suggesting that salvage pathway bottlenecks or mitochondrial membrane impermeability remain key barriers. Meanwhile, niacin, despite lacking a trendy mitochondrial label, has shown potent effects in immune cells where NAD metabolism plays a crucial role in both mitochondrial biogenesis and inflammatory regulation. In macrophages and T cells, niacin not only elevates NAD, but alters mitochondrial respiration and RLS balance, pointing to functional enhancement of mitochondrial activity. This occurs likely through a combination of systemic NAD rise and GPR109A receptor signaling, which influences mitochondrial gene transcription indirectly. This dual mode of action may actually offer broader mitochondrial benefits than localized precursor boosting. So, does compartmental superiority translate into clinical superiority? That's far less certain. The notion that NR/NMN are categorically better at replenishing mitochondrial NAD remains unproven in human trials. NR has not consistently improved mitochondrial oxidative capacity in skeletal muscle despite boosting NAD in blood. NMN has shown some promise in muscle insulin sensitivity, but mitochondrial-specific effects remain modest and transient. Clinical outcomes tied directly to compartment-specific NAD restoration, such as neurodegenerative progression, mitochondrial myopathies, or heart failure, have not shown dramatic improvements from NR/NMN supplementation. Moreover, focusing solely on mitochondria misses the point that aging and disease involve dysfunction across all compartments. Nuclear NAD depletion impairs DNA repair and epigenetic stability. Cytosolic decline disrupts redox balance and glycolysis. Mitochondrial loss affects energy production. A precursor that restores only one pool may offer temporary gains, but long-term resilience likely depends on broad, coordinated replenishment, which niacin, through its liver-centric, system-wide distribution, may better achieve. Finally, niacin's impact on NEAD, nicotinic acid adenine dinucleotide, a precursor and byproduct of the Price-Handler pathway, may contribute to tissue-specific NAD reservoirs in ways that are underexplored. NAD accumulates in some tissues following niacin intake and may act as a slow-release buffer for NAD regeneration, particularly under stress. This buffering is less evident with NR or NMN, which primarily affect the fast turnover salvage pathway. In conclusion, the compartment-specific effects of NAD precursors are real but complex, influenced by tissue enzyme expression, precursor bioavailability, and systemic feedback loops. NR and NMN may offer certain advantages in short-term cytosolic or nuclear boosting, but their mitochondrial edge remains theoretical, marginal, or inconsistent. Niacin, though less glamorous, delivers a systemic, steady-state NAD increase that reaches across compartments and may prove more clinically meaningful over time. Ultimately, the goal is not to selectively fill one pool, but to restore cellular NAD homeostasis in an integrated, sustainable fashion, something niacin is uniquely positioned to do when properly formulated and dosed.